Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 40, and we are starting chapter 11, part 1, which is interaction. Last time, we went over all the code in R for how to detect outliers and how to graphically test for the violation of linearity, homoscedasticity, and the independence assumptions. And we also assessed normality using a QQ plot, a special QQ plot of the residuals and the predicted values. And then we looked at the outlier test using these 6 different measures. And so we saw how to do that with code. All right. So in this video, we're going to talk about interaction. We're going to talk about 2 examples. One is going to be a generic example, and the other is going to be using actual data. Sorry about that. So, what is interaction? But before we get there, we're going to have to get this example and so that we define it. So we're going to study why is the growth rate of some organisms in some biological system. And it's affected by 2 independent variables. The first is going to be temperature, and the other is going to be a catalyst concentration. And we're going to study this 2 levels of each variable. So for temperature, we're going to look at T1 and T2. And then we're going to have catalyst concentration. It's going to be 2 different concentrations of catalyst. And so there's going to be 4 different levels examined: T0, C0, T0, C1, T1, T0, C0, T1, C1. And so let's look at these 2 graphs. So we're saying that there's no interaction in this graph. And I want to tell you and show you how to discuss and how to talk about this graph. So for this graph, we are fixing C0 at a certain value, okay? So we're saying, so this is T0, so this point here is T0, C0. And this point here is T1, C0, all right? So C0 is the same. What's changing is Y is changing. So we could say that at C equals C0, as T increases from T0 to T1, Y increases from, whoops, what happened there? Okay. Had a glitch with my iPad. It kind of stopped on me. From, whatever YA is to whatever value of Y is here. So we could say these 2 values, A and B. Okay? And then we could do the same thing for C equals 1. We could say at C equals C1, when T increases from T0 to T1, Y increases from whatever value that is to the new value. But when we look at this other graph here, this graph, we notice that the lines cross. Now, the important thing here is not just that the lines don't cross or that they're parallel, but that they're approximately parallel. And they're definitely going in the same direction. So we do not have to have the lines cross in order to have interaction. And there are some people that might be confused and tell you that that is true, but it's not. I can have this going on, and that is definitely interaction. If this is C0 and this is C1, as T increases from T0 to T1, the levels in Y at C0 decrease, whereas the levels in Y at C1 increase, okay? And so they're going in different directions. That is definitely interaction, okay? Now, when we have this parallel situation over here in A, we can just talk about C and T, okay? And in fact, when there's no interaction, we can just have one model here, and we can have the variable t and the variable c, and we can discuss t, what happens to y, or the mu of y, the mean of y, as t increases or decreases, and separately as c increases or decreases, okay? But, and so we often talk about the slope beta 1, the change in the mean value of y at whatever level of c. So we're going to choose a level of c, let's say that one, and so we have beta naught plus beta 2 c0 plus beta 1 t. And then we change and we have at the same, but for now c is 1, or c1. Okay. So what we mean by this is, let's say that we have y equals y hat equals beta naught plus beta 1, and I'm going to let t equals 1 for the first line, and c equals 1 plus beta 2, 1. And then I'm only going to change t. So t equals 2, and we're keeping c equal to 1. Then I have y hat equals beta naught plus beta 1 times 2 plus beta 2, 1. If I subtract the first equation, the whole thing, from the second equation, the beta naughts cancel out, and all I'm left with is 2 beta 1 minus beta 1. Everything else cancels, which is equal to beta 1. So the other way that we can do this, the interpretation of slopes are usually done this way. For a unit increase, that means an increase of 1 in t, so y, so for an increase in t, y increases or decreases. If beta 1 is negative, it will decrease, but if beta 1 is positive, then it will increase by beta 1 units. Okay? That is the interpretation of beta 1. Okay? And we're saying that we're keeping c constant in that case. We're just looking at beta 1. And we could do the same thing with beta 2. All right? Now, when there's no interaction, we should observe parallel responses or approximately parallel responses. Okay? So, in figure 1b, of course, we have the case with interaction, and we cannot describe it with that previous regression model. In fact, we need to, in order to describe this adequately, we have to add this interaction term, t times c. Okay? So now, if we look at this, a unit increase in t results in a beta 1 plus beta 1 2 c change in the mean of y. What are we saying here? Let mu of y given t equals 1, let's say, and c equals, we'll just call it c0, it doesn't matter. That is going to equal beta naught plus beta 1, t is 1, plus beta 2, c naught, plus beta 1, 2, and that is 1 for t, and then c0 for c. Okay? Now, we increase t by 1. T equals 2, c still equals c0, beta naught plus beta 1 times 2 plus beta, oh, this was 2, beta 2 c0 plus beta 1 2 times 2 and times c0. If we subtract these two, then again, these cancel, and I'm subtracting the first from the second, not the other way around. Then delta mu of y given t, and I'll say here, comma c, equals, this is 2 beta 1 minus beta 1. That's going to be beta 1 plus, and I'll have 2 beta 1, 2 times C0 minus 1 beta 1, 2 C0. And so that's going to equal beta 1 plus beta 1, 2 C0. So that's what we're doing to say, to get this here. That's how we got that, all right? And it depends on the level of C. So we have to have two equations, one for C0, one for C1. Now, when we're looking at this graph, we have to talk about T in terms of C. We can talk about T in terms of a fixed level of C1. So when C equals C1, as T increases from T0 to T1, Y increases or decreases here, decreases we'll call this A, we'll call this B. Y decreases from A to B. When C equals C0, as T increases from T0 to T1, Y increases from B to A, assuming that these are on the same level. And I know they're not, but we'll pretend for right now. Okay? So this increases, this decreases. So we cannot talk about T by itself. We cannot talk about C by itself. There's an interaction. We must talk about both of them. Now, I could reverse the graph. And I could say this is Y still, but now I've got C0 and C1. And for C0, I'm going to increase T0 to T1. I'm going to, let's see, so for T, I'm going to have T0 is going to increase. And for C1, C0's up here, C1's down here, so Y decreases as C goes from C0 to C1 for T1. So we can fix either one of these and talk about the other one, all right? And we can expand this to more than two variables, okay? But it's really hard. We can't graph it so easily, can we? Okay. So let's look at our age systolic blood pressure data, and this was for female subjects. And I want to really caution you, we do not ever discard data. This is a really bad practice. It's so bad that had I known this was in the book, I would not use this book. That's how bad of a error this is. We never throw away data. I want to make that clear. If you have a mistake, then you can get rid of the data point. If you have missing data, you can get rid of the data point as long as there's not, more than like 10% of the data missing, okay? But you don't throw away good data. And just because it's an outlier, okay, an outlier doesn't make it bad. It might be real data, and if you throw it away, you've lost information, and now your result is different. You can analyze it with the data point in there and then compare that to analyzing it without the data point in there, but never, ever throw away data unless you're positive and can prove that it's a mistake, okay? So just want to get that out there for you. Okay, so now, does the slope of the regression equation for systolic blood pressure on age significantly differ for males and females? So now we're going to look at this as, is there a difference between males and females? And so we're going to let female equal 1 and male equal 0. And here's how we write the equation. So if we want to combine this into one equation, we have to have a term for x, a term for z, and add this interaction Whoops. I'm not sure what's happening to my iPad here. Interaction of x and z. And so what we do is we're going to test for beta 3 equals 0. So it's h naught beta 3 equals 0 versus HA beta 3 not equal to 0 in the model y equals beta naught plus beta 1 x1 plus beta 2 x2 plus, I'm sorry, not x2, this will be x and z, right? So this is z, beta 2 z plus beta 3 x z plus e. Okay, and so in this case, I would use the type 3, the type 3 sums of squares, that test added last, okay? So I would suggest that as your test here because you don't want to use type 1, which is variables added in order, unless it's listed last. And it does happen to be listed last here, but it didn't have to be. It could have been listed first or second or what have you, but it does make sense to put that last. Okay, so first off, we can use our estimates and actually write the line. So when this is when sex is male or z equals 0, then when z equals 0, beta 2 is equal to, so this is our line. This is our overall equation line. So we've got our estimates here that we've plugged in to here and rounded to 2 decimal places. Now, when sex is male, or z equals 0, this goes to 0 and this term goes to 0. Both the interaction and the term, beta 2 term and the beta 3, everything that has z goes to 0, and we're left with this is our equation of only x. And when sex is female, z is 1, now these are no longer 1. I can take this value and combine them, and then I can take these and combine them because they both have x, so I have 2 different lines. If I look at this, this has a 0.95 slope, and this has a 0.96 slope, and they're graphed over here. And the slopes are very close to each other, but the question is, are they significantly different? And so this is our hypothesis test, so our test statistic, F equals, and I'm going to get that from right here, 0.01, with degrees of freedom equal 1 and 68. P-value equals 0.9342. Critical region. P-value, less than alpha, let's say that's 0.05. So we'd say 0.05 less than, so 0.9342 less than 0.05. That's not true. Do not reject H naught. There does not exist sufficient evidence to support the claim that the interaction between sex and age is significant in predicting the outcome Y, which is, what was this, systolic blood pressure, at a 95% confidence level, tested with N equals 69 subjects. Okay, so that is it for this video. I hope that I have adequately explained interaction to you. This is something you have to think about, and it helps if you draw this out and think about it and do what I just did through this video for yourself. Talk yourself through it and make sure that you understand it. Okay, please don't forget to scan your lecture notes by midnight of the date listed on the course calendar. If you have questions, come to my virtual office hours. If you can't do that, then by all means, email me. Send me a picture of your problem, send me a picture of your work, and I'll be able to help you through email. Of course, that doesn't prevent you from having to fulfill the requirement of coming to office hours once every 2 weeks. I'm just saying if you need help immediately and you can't wait until office hours, email me and I'm happy to help you. So please take care of yourself, stay safe, and we'll see you next time.